Hello beautiful people, this video is about the life cycle of a star. You have probably heard that we are all stardust. How does that come about? I'll explain in this video, so stay hooked on. And make sure you hit the subscribe button if you already haven't, and if you like my work, hit the like button and share this work as much as you can. And if you want to reach out to me, you can use the comment section below. I will always go through them. Now let's get started. As I said, the life of a star is cyclic. The point at which it starts is same as the point at which it is going to end, and it is at this point that I'm going to begin the story. This point, or this thing, is called nebula. It's a huge cloud of dust and gas particles. It's so huge that it can span light years across. Yeah, it's quite huge, of course. And the very important thing that starts the whole phenomenon is gravity, and the only thing gravity ever does is trying to collapse things to one point, and that's what it does here. It tries to collapse the dust and gas particles to one point, and it creates a ball of dust and gas particles, and the particles are in continuous motion. They keep hitting each other, but as time passes, the ball gets denser and denser, and the denser it gets, the more kinetic energy the particle gets while hitting each other, and at some point they are energetic enough for the electrons to be unable to stay attached to the nuclei. So electrons get stripped off and they create a plasma, and the core is formed only of the nuclei. So basically there is this core of nuclei and the plasma of electrons all around it, and the nuclei is now trying to hit each other, but they cannot because of the positive charge on the proton. It tries to repel the nuclei, but as time passes, the temperature of the core increases, and when it reaches around 15 million degrees, the nuclei are energetic enough to actually hit each other, and when they do not separate, they stick together, they fuse, and this thing is called nuclear fusion, and this releases a crazy amount of energy. This energy is absorbed by other pairs of nuclei and they start fusing, and this sets off a chain reaction, and the energy that is not absorbed by any pair of nuclei moves towards the surface, and the surface particles radiate them in the form of electromagnetic rays, which are mostly electrons. A star is born, a star has started to shine, a journey has begun. And the size and the color of the star could vary widely. The size could vary from half as massive as our sun to 20 times as massive, and the color could vary from anything like blue to red. And this depends on the temperature, surface temperature of the star, which in turn again depends on how massive the star is. So the mass of the star is a very key parameter which determines almost everything about the life cycle of a star. We'll keep getting back to this, so make sure you get the idea quite well. The star has been born, quite good, but what now? Of course it has to use some kind of energy to stay alive, like everything needs. And this energy comes from the nuclear fusion that is going on at the core. Hydrogen nuclei and helium nuclei keep fusing to form higher, heavier nuclei, and this keeps the star alive. How? The nuclear fusion releases energy which tries to explode the star outwards, and the gravity is trying to collapse the star. So there is a balance between the nuclear fusion and the gravity, and the star keeps on living. This could be millions and billions of years, but at some point the fuel is going to run out. There won't be any more hydrogen or helium nuclei. What then? The star will start to die. Yeah, the end is near. Now, as the fuel has run out, the nuclear fusion has stopped. Gravity is the dominating force. It is trying to collapse the star towards the core. But as this collapse occurs, the heat, the temperature and the pressure in the core go up again, which again tries to explode the star. And this is temporary, but it is powerful enough to expand the star from a few times to a few hundred times the size that it has ever been before. This phase is called the red giant star, but it has to come to an end, as everything has to. So in the red giant star, the star has expanded, but the outer layer is mostly plasma, electrons and lighter particles, lighter nuclei, and the core is usually made of the heavier nuclei, and it starts to collapse all over again due to gravity. And it is at this point that another phase starts, but this changes for how massive the star was initially. If it was something under or up to 1.44 times as massive as our Sun, we would call it lowly massive star. If it was something between 1.44 times the mass of our Sun to 15 times as massive as our Sun, we would call it moderately massive star. And if it was more than 15 times as massive as our Sun, this would be highly massive star. Let's take a look at the lowly massive stars first. So the core collapses, and the collapse increases the temperature and the pressure at the core, and the nuclei start fusing all over again, and it releases a tremendous amount of energy. This is a slow process. It takes quite a few years, but this phase is called white dwarf star. It is quite dense. It is supposedly the second most dense substance in the universe, the white dwarf star. But how far can this go on? The nuclei are fusing hydrogen and helium to lithium, beryllium, boron, carbon. That's it. No further, because carbon is quite a stable nuclei. It cannot fuse to higher nuclei anymore. So as more and more nuclei turn into carbon, the last remaining bits of the fuel is starting to die out. And at some point all the nuclei have to be turned into carbon, and there won't be anything to fuse. That's the end of the star. We call it a black dwarf star. It's just a huge mass of carbon in outer space. It doesn't radiate any light, nothing. It's just a dark ball of carbon. That's the end of the star. That's a black dwarf star. Now let's take a look at the second phase, moderately massive stars. As the nuclei collapse, if the star was moderately massive, it would have enough gravitational collapsing force that it would make the atoms nuclei fuse even beyond carbon up to iron, which is the next stable nuclei. And as more and more nuclei turn into iron, the core gets heavier and heavier as the heavier nuclei tend to be around the center. And as the gravitational collapse continues, there is quite a bit of collision between the iron nuclei, which sets off a shock wave, and this shock wave travels from the core of the star towards the surface. This phase was called the neutron star. Or should I say, this phase is the starting of the neutron star, because as the shock wave moves from the surface, it tends to strip off the lighter nuclei, and all that remains is huge ball of iron nuclei so far. And gravitational collapse again continues, but this time it doesn't fuse into other nuclei. Instead, the electron and the proton fuse into each other and form neutrons, and this ball that is left behind is nothing but a huge mass of neutrons. And this is the most dense substance known in the universe, a neutron star. And the process of the shock wave stripping out the lighter nuclei is called nova. Now let's look at the heavily massive stars. The process is similar until the shock wave, but once the shock wave is initiated, it is quite powerful this time, much more powerful than the nova, and this is called a supernova. And what is left behind starts to collapse all over again, but this time the gravitational pull is so strong that not even neutron star is a stable form. This time eventually it turns into a black hole. And let me tell you one more thing. I said it was a weird number somewhere in between, 1.44. This number was discovered by an Indian physicist Subramanian Chandrasekhar, and he was awarded the 1983 Nobel Prize for this. This number is the limit up to which, in terms of the mass of the solar mass, a star could form white dwarf stars. Beyond this, white dwarf stars are not possible. It is either neutron stars or black holes. That's it for today. Keep loving physics.